Remember when we first started talking about confidence intervals, we sort of had this Goldilocks problem. How big should we make the confidence interval? We know it's going to be centered at p hat, but how much should we widen that estimate in order to guarantee that we capture our population proportion? Now, if you go too big, then you're losing information about the actual population parameter. So for example, I can be 100% confident that the proportion of people with blue eyes is somewhere between 1% and 99%. But unfortunately, that doesn't give me much information about that true population proportion. On the other hand, if I go too small and say the proportion of people with blue eyes is somewhere between 33.3% and 33.4%, right? It's very unlikely that I've widened that confidence interval wide enough, and I'm actually capturing the population proportion with the confidence level or with the success rate that I'm hoping to achieve. So we have to answer this question, how wide is just right? And in order to do that, in the case with the sample means, we looked at the sampling distribution of the statistic we were actually collecting. We're going to do the same thing when we're thinking about this for our for our sample percentages. So let's use the following simulation to get a sense for what the sampling distribution of sample percentages would look like. In other words, let's assume we have a population like this. Now, just for visualization, I've sort of set it up so that all of the yes answers are to the left, all of the no answers are to the right. But the selection from this population is going to be random, so that won't have an effect. You can see that you can modify your population percentage if you want to run this with some other values. For now, let's leave it at 0.4. And what we're going to do is each time I click one of these get one samples, I'm going to get a random sample, right? Again, we're circling the dots that ended up appearing in the random sample. We compute a sample percentage, and down below we're keeping a log using a histogram of the sample percentages that have appeared so far. So we've already collected two random samples, which led to two different sample percentages. And now we're going to collect some more. And we're keeping track of the histogram for this thing. And as we saw when we were looking at the sampling distribution for x bar, the sampling distribution for p hat, a sample percentage, we can start to reveal what it'll look like by just keeping a histogram of, say, maybe 1,000 different samples. So we'll see as we collect, I don't know what that was, maybe 700, 800 different samples, and we now look at a histogram of what would be 800 different sample percentages, we can start to see the shape that the sampling distribution would roughly start to take. The first thing we notice here is that this has a nice normal shape to it. The second thing we notice is that the tallest bar is right around 0.4, which ends up being our population percentage, right? So this sort of gives us justification that the sample percentage is, in fact, a good estimator of the population percentage, because it's most likely that your sample percentage is going to be right near your population percentage. We obviously do have a certain amount of variation, which we'll be able to quantify with a formula I'll show you in a little bit. But the general idea here is that this thing looks like it has a nice normal distribution. The peak is going to be at the population percentage, and that standard deviation, how much variation we see in these p hat values, we're going to have a nice formula to compute that. So the idea behind answering this question of how wide do we make these? Well, we're still going to choose, in a sense, a length based on the variation in the p hat values. And so that's what we're going to see when we get a modified version of our margin of error formulas. One small technical note, technically the distribution of these p hats is not a normal distribution, but it's close enough so that we can approximate it well using a normal distribution. So that's what we're going to do. Since we're familiar with the normal distribution, the standard normal distribution, we're going to end up using that as our probability model because it's a good enough approximation of what actually happens with the sampling distribution of p hat. Okay, I think we're ready to outline the steps and the slight modifications we're going to make to determine a confidence interval for a population percentage. First, we're going to assume that we're given a confidence level, or we as a researcher would choose the confidence level. Remember, this is the success rate that we want to have for this process. So what percentage of the confidence intervals I could get, right, by taking a random sample, actually overlap with that real population percentage? In addition to that, we're going to have sample data that is either given to us or that we've collected as researchers. From the sample data, we need to compute two statistics: the sample size, and then typically we're going to have to use a counting function to figure out how many people have the characteristic we're looking for. How many people said yes? How many people like mango ice cream, etc. And from those two, we compute a sample percentage. Remember, this is our best guess for what the population percentage is, but we're going to widen this with a margin of error to increase our likelihood of capturing that population percentage. We're still going to need a critical value, but we're back to using the standard normal distribution as our model. So rather than computing a t alpha over 2, we're back to using a z alpha over 2. But otherwise, this process is exactly the same. Remember, we use norm.s.inverse to get these z critical values. Finally, we have our margin of error formula. It's our critical value, our z critical value, times this kind of complicated thing I'll call a square root term. We're typically going to compute this separately just so that we don't make a mistake in our typing in Excel. But this complicated square root term, in fact, is a good estimate for the standard deviation we would see in the sampling distribution for p hat. So that histogram that we looked at in the previous case, right? A good estimate for how much variation is in those that histogram of p hat values is given by this sort of square root term. We take our sample percentage, we multiply by 1 minus the sample percentage, make sure this is in parentheses, divide by n, and then we square root that whole number. So we'll go over how to do this in a little bit more detail once we're working in Excel. Lastly, remember, since p hat is our point estimate, it's our best guess for what our population percentage is, that's going to be the center of our interval. And then we want to move our margin of error to the left and our margin of error to the right to get the left and the right-hand bounds. So our actual confidence interval ends up looking like p hat minus e and p hat plus e. One last comment before we move on to our next example. Notice how similar the steps of this confidence interval are to when we were computing a confidence interval for a population mean. Right? Basically, we're given data, we choose a confidence level or if it's provided. From the sample data, we compute relative or necessary statistics to help us determine our margin of error or the center of our confidence interval. We get a critical value. Our margin of error consists of the critical value times an estimate for the standard deviation of that sampling distribution. This is sometimes in statistics called a standard error. But we have nice formulas for this, and these formulas are provided on each one of the exams. And then finally, you create your confidence interval by using your point estimate, which is your sample version of the parameter you're trying to estimate. And then we subtract, or we add, the margin of error to get either the left or the right-hand point. So this is consistent whether you're doing a confidence interval for a mean or for a population percentage. But you do have to kind of keep track of the small little changes like what's that standard error formula, do we use a z or a t critical value, etc. What's the center of the confidence interval? So please keep these things in mind. Study both of the confidence intervals together and kind of explain how they're the same and how they're different. It'll help keep things straight in your mind. Let's consider our first example for today. I want you to know that in our W10-D3 Excel workbook, both of the examples we're about to go over are there, and this is where we're going to record most of our work. So please keep this in mind moving forward. You may want to open this up and get ready to do the example along with me. So let's read through. Suppose we're interested in the percentage of all college athletes that get physical therapy for a recurrent injury. To estimate this, we'll run a sample survey and construct a confidence interval. We select a simple random sample of 85 athletes, right? So we're working with a sample, not the entire population of college athletes. And then we're going to give them a survey. We're going to record whether they get therapy for a recurrent injury or not. Apparently, of those that we surveyed, 68% do get physical therapy for a recurrent injury. Using a confidence level of 92%, we want to create a confidence interval to estimate the upper and lower bound for the population proportion. Right, so we're doing a confidence interval for the population proportion of athletes receiving therapy. So this isn't the same as our 68%. This is our sample percentage. We want an interval that estimates the population proportion. If we could access all the college athletes, what would the proportion in that population be? We can do this using our process. So I'm going to put the steps back up, and we're just going to walk through this line by line and start filling in some information. So notice we're given a confidence level and some sample data. In this case, rather than being given the data, we're actually given the statistics that we need. Remember, n is our sample size, and in this case we have 85. P hat, if you want to leave yourself a little comment here, this is the sample percentage. And typically this is the number with the desired criteria or condition, characteristic maybe, divided by sample size. So we may have to compute this, if we have the raw data, we may have to actually compute this using Excel. But in this case, we're told that 68% of the sample that we collected gets physical therapy for a recurrent injury. So our p hat value in this case is 68%. We're also told that the confidence level that we want to work with is a 0.92. Now, what I want to do is first determine our z alpha over 2, our critical value. So keep in mind, from our confidence level, we use our usual process. And then when we know we're doing a z alpha over 2, we use norm.s.inverse to compute our value. So if alpha is the missing percentage, we can do 1 minus confidence level. So we have 8% that needs to go in the two tails. Take that 8%, divide it by 2. So we have 4% in each tail. And then keep in mind, again, we can insert a comment. This is the z-score with a probability of 1 minus alpha over 2 to the left. And just as a little reminder, if we know a probability to the left and we want to compute the score, we use the norm.s.inverse function. So we're going to type in norm.s.inverse 1 minus alpha over 2. That's the area to the left. And now when we hit enter, we'll get the appropriate z-score to use. Okay. Now, in our next step, we want to compute this square root term because we're going to take our z-score times our square root term in order to get our margin of error. So let's leave ourselves a note for what this square root term actually looks like. So this is going to be equal square root p hat times 1 minus p hat divided by n, and then we're going to close our square root. All right. Now keep in mind our p hat is in a cell, so we can just cell reference this as we're putting the formula together. And this follows the same formula we have over here. We have a square root over the whole collection of what's inside. This is p hat times 1 minus p hat divided by n. So as we're filling out our square root term, let's follow this guide. Square root, open your parentheses, take p hat times another set of parentheses because we want the 1 minus p hat to be computed first before we do the multiplication. And then finally, we're going to divide by our sample size and close our square root function. So this is our square root term. Now our margin of error, in the way that we're breaking up our work here, E is just going to be z alpha over 2 times what we've been calling our square root term. So all we need to do is use cell reference these two cells and look at their product. And keep in mind, this is exactly what we're doing to compute the margin of error on this other side. Right? We've got our z alpha over 2, that's our critical value, and then this square root term we just put in a separate cell. So we'll do equals square root term, or let's be consistent, we'll start with our critical value times the square root term. This is, again, sometimes called the standard error for our sampling distribution for p hat. And we get an e value of 0.088. So this is telling us that the margin of error that we're going to use to widen away from our sample estimate is about 9%. So to create our confidence interval, we're going to start at p hat, and we'll subtract our margin of error. And then to get the other bound, we'll start at p hat, and we'll add the margin of error. And the idea is that we can be 92% confident that the percentage of all college athletes treated for a recurrent injury falls between, let's say, 59.1% and 76.9%, where we'll round.